Okay. Well, let's see what is the relationships between these two, and that this will make this last definition a little bit more concrete. So first is, what is the strongest one of these? Well, if f is differentiable at x bar, these functions, they are contained, so all such functions also have directional derivatives. And it's a strict inclusion. There are counterexamples. And partial derivatives is the weakest one. And you can find examples of any one of these failing. So you can have a differentiable, one with directional derivatives that's not differentiable, one with partials that doesn't have directional derivatives, and also one that has these two, but not that. Yeah, any form combination of these that respects this inclusion relationship. And another thing worth knowing, and we'll talk about Friday about how to prove this, is that the only one of these three that implies continuity is the differentiability. So f differentiable at x bar is contained in those functions that are just continuous at x bar. And this is again strict. You have not differentiable functions that are continuous. But these things lie outside of that hierarchy. So these need not be continuous. And this is one of the reasons why this notion, even though it's the most technical of them to state, partial derivatives is the easiest one to state, but it's also the weakest. The one that's hardest to state and conceptually the most difficult, it's the only one that gives you continuity, and that's why one of the many reasons why you actually have to use it. There are other reasons, such as chain rule only works if you have differentiability. Change of variables only works if you have differentiability. So usually you have to assume differentiability. These are mostly useful to clarify how these hierarchy is done. But in this hierarchy, I mean, there should be a way of recovering the directional derivatives from the full derivative and the partial derivatives from the derivative. So if f is differentiable, well, we have the derivative is given by this map ax bar h. And using that map, we can express actually all these other derivatives. So the directional derivative of the function is just the same thing as ax bar of v. The partial derivatives of f are just ax bar of ei. And this linear map that looks kind of abstract as a combination of these two things, a little bit of linear algebra, that is actually given by an inner product between the gradient and v. So in the differentiable context, we don't actually have to talk about general or linear maps. We can just talk about gradient of f dot v. And that's where kind of these three come together in this way. Now, directional derivatives, all we can say is that partial I of f is dEi of f. We can't say anything more than that. For example, we cannot say that the directional derivative dvf need not be equal to gradient of f dot v. It's only true if f is differentiable. So in this case, when you only have directional derivatives, you don't have to have the derivatives in the inner product of the gradient of v. And these theorem statements, I want to conclude just by, so all of these kind of the bad cases, borderline cases. But the good thing is that the strongest one of these conditions, differentiability, you only need, it's fairly easy to verify from the weakest one if you add something to it. So if you have a function whose partials exist, and if the partials are continuous, then you know that it's differentiable. So this is kind of the good case where everything collapses. There's only one notion of derivative. So let's look at some examples. We don't have, I don't think it's worth even doing these calculations in this lecture. They were written in, are written in the notes. I'll just show you the pictures, what these look like. So what does a differentiable function look like? Well, this is a simple function, x times y, its graph. If you zoom in, then what you get is a plane corresponding to the linear function that approximates the function. It's flatter and flatter. And the derivatives in these different directions become a combinations of the other, and that's where the linear structure comes out. And we also see that we are becoming continuous because there's no weird jumps in this graph. But let's change this function a little bit. Let's change it to xy divided by x squared plus y squared. Okay, let's see what that looks like. And I want these grid lines. Okay, whatever. Now the origin here lies at this point. And what you see is this sort of dumpling-like shape. This is the origin here. And along some directions, your function is approaching 1. But along other directions, it's approaching 0. So the function is actually not even continuous. It's jumping from 0 to 1 in this very small neighborhood. But if you look only in the coordinate directions, you'll find that actually in the coordinate directions, everything will be differentiable. Coordinate directions here lie on the y direction and the x direction. And in those coordinate directions, it's not quite clear from this picture, the function is actually equal to 0. If you look at the formula, you see that here. When x or y is equal to 0, the function is just equal to 0, so it's completely flat. But you've kind of pinched these shapes in different quadrants in different ways. So this is an example of something with partial derivatives existing, but which is not continuous. And if you look carefully, it actually does not even have, it does not have directional derivatives in all directions. Now let's modify this a little bit, this example. Let's multiply it by x. So let's make it convert. So what happens in that case? So zoom out. Okay, now we're getting this good picture. So now this is the behavior at 0 when we multiply by x. Well, now it has become a continuous function. Multiplying by x made the folds kind of push them towards 0. And this function still, if you follow the axes, you see that the derivative in that direction is 0. The derivative in that direction also is 0. But then in the diagonal directions, you don't get derivative 0. In these diagonal directions, the directional derivative is not 0, even though the partial derivatives are 0. So that's already a warning sign. So you cannot have gradient.b. This formula is fundamentally against that. And geometrically, if you zoom in, you're not getting a plane. No matter how far you go into this picture, you're just sort of seeing the same thing. It becomes this kind of conical thing. It's actually self-similar. strictly speaking. So it's not differentiable. So this example, the exact properties are listed on in the notes. This example shows you that you can have all directional derivatives there. You can be continuous, but not differentiable. So somehow the directional derivatives don't control the function. And the final example, and this I have to say a small caveat about, but let's write the formula first. So actually the 6th plus y cubed. And 6 plus y. Oh no, that's right. Let's see. Okay. This is stupid. This is not focusing on the origin. So, okay. So now we are here. And this is almost complete. So yeah, now we start seeing this behavior that's interesting. So there's a weird thing. You should disregard what happens on this side. Right. Why that is happening is that this denominator is infinity, or denominator is 0, so the thing is infinity. And there's a way to change that. You can make the function value 0 on that side. What you should focus on is what's happening on this other side. And it's quite hard to see, so I recommend maybe you try this yourself. The simulation is not as nice as it initially was. So in this case, what is happening is that you have all directional derivatives. You have all directional derivatives. All of the directional derivatives are equal to 0. All the partial derivatives are equal to 0. Yet the function is not even continuous. There's this ridge here along which if you approach, so again on a quadratic way, similar to the example that we get, you actually fail continuity. So this kind of example where a curved shape appears is one where the way you're approaching 0 matters. So this is the most subtle way that differentiability can fail. So on Friday, we will talk more about that differentiability limit condition. We'll see how it relates to continuity, and that will give a better sense of what it looks like. And then we will conclude by proving this theorem about the continuous partial derivatives.